Hi everyone, so for today's video we're going to be looking at limits at infinity. Now you should have looked at the infinite limits notes first, and the reason is because when we did the infinite limits, if you recall, the dependent variable or the y values became very large, usually went to infinity or negative infinity as x approached a specific number. Okay, so if you recall, we actually used the same function here. We were looking at what happened around this vertical asymptote. Okay, now with limits at infinity, the opposite thing occurs. So now we're looking at, when the x value or the independent variable approaches infinity or negative infinity, the y value or the dependent variable approaches a specific number or a finite number. Okay, so for the infinite limits, we were focusing around vertical asymptotes, but for today, for limits at infinity, we're going to be looking at horizontal asymptotes. Okay, and so in this graph in particular, you can see that as we approach infinity or negative infinity, so let me start here. So if as the x values approach in positive infinity, that's like looking this way. Notice the y values are approaching a specific number. So in this case, the y values are approaching the x-axis, which has a y value of 0. All right. Likewise, if I were to approach negative infinity, so as the x values get smaller and smaller, go to negative infinity, the y values are also approaching 0 in this particular graph. Okay, and we can see it in the table too. So if we read the table down like this, notice as x gets bigger and bigger, right, the independent variable gets large or heads towards infinity. What happens to the y value? Well, the y values get closer and closer to 0. So, limits at infinity, like I said, we're basically looking at horizontal asymptotes. It says if f of x becomes arbitrarily close to a finite number L, for all sufficiently large and positive x, then we can write this notation. Now remember, that's how we read it. This is saying as, the limit as x approaches infinity of the function f of x is equal to L, so L is a finite number. We say that the limit of f of x as x approaches infinity is L, and that in this case, really what we're saying is that there is a horizontal asymptote, and what is that horizontal asymptote? It's y equals whatever that number is. So in this case, whatever L is. Okay, so let's, again, the best way to explain this is to do some examples. So it says evaluate the following limits. All right, so we are going to kind of break this up. So the first thing I'm going to do is, this is really the same thing as the limit as x approaches infinity of 2 plus the limit as x approaches infinity of 10 over x squared. Alright, so, and you can also sketch the graph. In fact, maybe that's what I'll do as well. Just a quick sketch here. So, if you were to graph this, you will see that there is a horizontal asymptote there, and the function kind of looks like this. Not drawn perfectly to scale, but we're just drawing a sketch here. So I know you can read the graph and you can say, oh yeah, I know what the limit is, right? But if we're going to do it algebraically here, the first thing I've done is I split it up. And if I look at this first part here, well, notice there's no x value there, so the limit as x approaches infinity of 2 is just 2, okay? And then plus, we got to look at what's happening over here. So as x gets larger and larger and larger, so let's think about this. Suppose we have an x value of like 100. Well, 10 divided by 100 squared, right, would give me a big number. What happens if x is 500 or 1,000? So as x gets bigger and bigger and bigger, you will see that the overall fraction here, 10 divided by whatever that number squared is getting closer and closer to 0. So this limit really is 0, right? It's approaching 0. And so the overall limit, it would be 2 plus 0, which is 2. So likewise, we're going to do the same thing for part B. You don't need to draw the graph, right? We're going to kind of use the same reasoning here. So I'm going to split it up into two pieces. So I have the limit as x approaches infinity of 5 plus the limit as x approaches infinity of, sine x over x squared of x. So same reasoning. If I look at this first part, the limit as x approaches infinity of 5 is just 5. And then if I look at the second part here, we're going to kind of use the same reasonings. As the x values get bigger and bigger and bigger, what's happening to this fraction? Okay, so if you are having a hard time seeing what that is, it's okay to plug in values, right? So try when x is 100, then try when x is 1,000, or whatever, and see what's happening to that overall fraction. And hopefully you'll see that that also kind of gets closer and closer to 0. So that means the overall limit is 5. Now if I were to sketch this graph, there's some sign in there. So the sketch of that one would look like, let's see, if I 1, 2, 3, 4, 5. So there is, the graph here that is kind of like hovering around that 5. But like I said, you should be able to do it algebraically as well. And so what we're trying to say is, okay, if f of x becomes arbitrarily large, so if the y values become very, very large as x becomes very, very large, right, then we use this notation. So the limit as x approaches 0, or x approaches infinity, if f of x is infinity. And really, I know this is probably a little intuitive in some ways, but you've actually done this a lot in pre-cal, but we used a different phrase to describe that. But the behavior of a function as x approaches positive or negative infinity, right? So if I look back at this graph, like we're looking at what's happening over here and what's happening over here. In the past, we have called it, let's see if I can scroll down some more, we have called it end behavior. So really, we're looking at end behavior. What's happening as x gets very, very large or very, very small. And that is it for these set of notes.